All right, what's going on, my people? I'm just tuning back in to do a bit of a read along uh, for my CISSP studying. So I've been reading CISSP study guide, and I'm on domain 8 right now and reading chapter, I believe, 19 or 20. Let's see what chapter this is. Yeah, chapter 20, software development security. So we get into the part of cybersecurity that I'm actually the most familiar with. And this is exciting. I like it. I know the coding. Everything else was still a refresher, but there were a lot of things that I was learning new. A lot of this, I'm sure, will be primarily a refresher. Introducing system development controls. Many organizations use custom developed software to achieve their unique business objectives. These custom solutions can present great security vulnerabilities as a result of malicious and/or careless developers who create backdoors, buffer overflow vulnerabilities, or other weaknesses that can leave a system open to exploitation by malicious individuals. To protect against these vulnerabilities, it's vital to introduce security controls into the entire system's development lifecycle. An organized methodical process helps ensure that solutions meet functional requirements as well as security guidelines. The following sections explore the spectrum of systems development activities with an eye towards security concerns that should be foremost on the mind of any information security professional engaged in solutions development. I'm actually an information security professional to my job right now. So this is very much speaking the language and the things that I need to know day to day. Security should be a consideration at every stage of a system's development, including the software development process. Programmers should strive to build security into every application they develop, with greater levels of security provided to critical applications and those that process sensitive information. It's extremely important to consider the security implications of a software development project from the early stages because it's much easier to build security into a system than it is to add security to an existing system. So one of the, I guess, concepts that keeps coming up at my current firm is secure coding. And there was a whole training process giving to the developers and a bunch of courses available to train developers on how to securely develop their applications and new features. I didn't actually go through that program because I'm not considered a developer at the company, but from my perspective, some of those techniques and skills that you need to understand are, well, you one of the things that we're really trying to push the teams on, or the application development teams on, is using the tools that they have like SonarQube, or we use Sonatype and Web Inspect and Fortify, though that suite of products, to actually keep an eye on the vulnerabilities that you're introducing when you create a new feature. So that would be from the application development standpoint, and that doesn't cover anything related to the infrastructure, right? Your application can be as secure as it wants to be or as secure as you need it to be. But if you have insecure infrastructure, like misconfigured S3 buckets, or ports that are open when they don't need to be open, or you're running a version of some Kubernetes node that has known vulnerabilities, all of these things can negatively impact the security posture of the entire system. So that's a different consideration. That's not really secure coding. That's more infrastructure security, platform engineering, things like that. Application security, secure coding is just making sure you're not using insecure practices inside of your code. As you probably know, software developers use programming languages to develop software code. You might not know that several types of languages can be used simultaneously by the same system. This section takes a brief look at the different types of programming languages and the security implications of each. Computers understand binary code. They speak a language of ones and zeros, and that's it. The instructions that a computer follows consist of a long series of binary digits in a language known as machine language. Each central processing unit, CPU chipset, has its own machine language, and it's virtually impossible for a human being to decipher anything but the simplest machine learning code, machine language code, without the assistance of specialized software. Assembly language is a higher level alternative that uses mnemonics to represent the basic instruction set of a CPU, but it still requires hardware specific knowledge of a relatively obscure language. It also requires a large amount of tedious programming. A task as simple as adding two numbers could take 5 or 6 lines of assembly code. That is crazy. Programmers don't want to write their code in either machine language or assembly language. They prefer to use high-level languages such as Python, C, C Sharp, C++, Ruby, R, Java, and Visual Basic. I use Go and Python for all of my apps. And Flutter. Or Flutter is the framework. I use Dart. That's the language. I think Go and all of the languages I just mentioned, Go, Flutter, and Python, or Go, Dart, and Python, are all built off of C++, or at least the compilers for Go and Dart are built on C++, and the interpreter for Python is built with C++. I'm going to fact check that though. I'm pretty sure that's the case. These languages allow instructions that better approximate human communication, decrease the length of time needed to craft an application, possibly decrease the number of programmers needed on a project, and allow some portability between different operating systems and hardware platforms. Once programmers are ready to execute their programs, two options are available to them: compilation and interpretation. I just thought about something too with this. So there was a time when assembly language and machine languages were the only programming languages available for developers. And there was a set amount of applications and software that was developed at that time because it was just so difficult for new developers to be trained on those languages. When we started getting more higher level languages like the C's, the C sharps, and all of these, we got more developers. So I imagine that same process to happen now when we get better software, like AI helping people write more software. We'll probably end up needing more software developers over time because now you're just gonna look at and see more things that we can build. Some languages such as C, Java, and Fortran are compiled languages. When using a compiled language, the programmer uses a tool known as a compiler to convert source code from a high-level language into an executable file designed for use on a specific operating system. This executable is then distributed to end users who may use it as they see fit. Generally speaking, it's not possible to directly view or modify the software instructions in an executable file. However, specialists in the field of reverse engineering may be able to reverse the compilation process with the assistance of tools known as decompilers and disassemblers. Decompilers attempt to take binary executables and convert them back into source code, whereas disassemblers convert back into readable languages, machine readable assembly language, and intermediary step between an intermediary step during the compilation process. I'm currently trying to stop my dogs from fighting and or licking each other. They're being weird under the table. So I'm getting distracted. Sue me. These tools are particularly useful. Oh, we just said nighttime. They said take it back to black. Alright. These tools are particularly useful when you're performing malware analysis or competitive intelligence, and you're attempting to determine how an executable file works without access to the underlying source code. Code protection techniques seek to either prevent or impede the use of decompilers and disassemblers through a variety of techniques. For example, obfuscation techniques seek to modify executables to make it more difficult to retrieve intelligible code from them. In some cases, languages rely on runtime environments to allow the portable execution of code across different operating systems. The Java Virtual Machine, JVM, is a well-known example of this type of runtime. Users install the JVM runtime on their systems and may then rely on that runtime to execute compiled Java code. Other languages such as Python, R, JavaScript, and VBScript are interpreted languages. When these languages are used, the programmer distributes the source code, which contains instructions in the higher level language. When end users execute the program on their systems, that automatically triggers the use of an interpreter to execute the source code stored on the system. If the user opens the source code file, they're able to view the original instructions written by the programmer. Mm, I've always heard that compiled languages are also faster to run and maybe potentially smaller because you're storing just a binary file versus if you're running a Python project, you need to store the entire source code, which could be larger. The JVM takes a lot of space on its own though, as that type of language. I think Golang is a preferable language to JavaScript, or not JavaScript, to a compiled language like Java because you don't need the JVM. So you can just get the Go compiler and it'll convert your code into binary that can a binary executable that can run on any platform. And you don't have such a large operating system or runtime like JVM. And it also is incredibly quick to run. Like it's faster. I don't know. I've never compared Golang to Rust, but it's much faster than running a Python language. Or that's at least that's what they say. I gotta actually run some benchmark tests to determine if that's really the case. But it makes sense in a way. Each approach has security advantages and disadvantages. Compiled code is generally less prone to manipulation by a third party. However, it's also easier for a malicious or unskilled programmer to embed backdoors and other security flaws in the code and escape detection because the original instructions can't be viewed by the end user. I think this is more important in like a B2B company where you're taking some code from another developer or an external developer and running it inside of your environment. That code that you bring in, you have to trust that it's doing exactly what the developer or the vendor said it does and nothing else. And so if you're taking a compiled binary, you're not able to see very easily what instructions they put in. So that's not good for you. From the vendor's standpoint, it's much better for them to give you a compiled executable than to give you the source code, because if I'm charging you for the code, then if you have the source code, you don't need me anymore. So that's the benefit there for them. Interpreted code, however, is less prone to the undetected insertion of malicious code by the original programmer because the end user may view the code and check it for accuracy. On the other hand, everyone who touches the software has the ability to modify the programmer's original instructions and possibly embed malicious code in the interpreted software. You'll learn more about the exploits malicious actors use to determine software, to undermine software, in the section Application Attacks in Chapter 21. Malicious code and application attacks. Libraries. Developers often rely on shared software libraries that contain reusable code. These libraries perform a variety of functions ranging from text manipulation to machine learning and are a common way for developers to improve their efficiency. After all, there's no need to write your own code to sort a list of items when you can just use a standard sorting library to do the work for you. That is facts. That's a fact. But you should at least attempt to implement some of these common sorting functions and data structures. I think that's a good learning lesson. Something that I did a lot when I was in college, when I took my data structures classes and data algorithms. We implemented sorting functions, like we implemented bubble sort. We implemented uh, bubble sort, merge sort, quick sort, like all of that in code with, I think we use C++ at the time. But there were other functions that could do that. Well, you wouldn't really do that in real life, in a real world project, but it helps you to practice and learn those algorithms and the time complexity of them when you write it yourself. And same for when you're implementing a data structure like a map or a list, a linked list, something like that. When you have to create what a node is, that class, that object, or the class, not the object. Instance of it is an object. Many of these libraries are available as open source projects, whereas others may be commercially sold or maintained internally by a company. Over the years, the use of shared libraries has resulted in many security issues. One of the most well-known and damaging examples of this is the Heartbleed vulnerability, CVE 2014-0160, that struck the OpenSSL library in 2014. The OpenSSL library is a very widely used implementation of secure sockets layer and transport layer security protocols that was incorporated into thousands of other systems. In many cases, users of those systems had no idea that they were also using OpenSSL because of this incorporation. When the heartbeat when the heartbleed bug affected OpenSSL libraries, administrators around the world had to scramble to identify and update OpenSSL installations. To protect against similar vulnerabilities, developers should be aware of the origins of their shared code and keep abreast of any security vulnerabilities that might be discovered in libraries that they use. This doesn't mean that shared libraries are inherently bad. In fact, it's difficult to imagine a world with shared libraries aren't widely used. It simply calls for vigilance and attention from software developers and cybersecurity professionals. So, one of the things that you can do as a professional to make sure you're protecting against the problem that is being uh, described here is to create a secure software bill of materials for all of your applications. And if we think at the product level, that could be pretty difficult to think about. But if you think about a specific application, whether it's a UI project or an API or some other script, whatever that component is that you're building and coding, think with like your code base, that project should have a very clearly defined dependency list. You should know the exact versions of any dependencies and the names of those dependencies. And that should be checked in with the code and something that can be monitored and tracked over time. Additionally, you should be scanning your code bases, or not even just the code bases. I mean, you can scan the code base to identify static vulnerabilities, like just, I'll say, poor coding practices, but you should also be scanning the builds of your project. Like you should know, yeah, you should know. And I wonder if you don't need to actually build the application to scan the dependencies. So never mind. You don't need to scan the builds. You need to scan the projects, like the actual code base itself. And you can set up scanning with a tool like with SAST tools, uh, static, uh, static assessment security tools, or SCA, which is security. Mm, it's like security code analysis. I think it's that. Let me confirm before I start lying. Software composition analysis. Yeah. Yeah, so that mm, so the SAST tools will scan your code that you wrote without running the code. An SCA tool will scan the third-party libraries and dependencies, which are the same thing. Shared libraries, dependencies, third-party libraries. These are all something that you import into your application that you didn't actually build yourself. And it'll scan those versions, or it'll scan the versions. Hmm, I'll say it'll not even scan it. It'll scan the dependencies that you have and check to see which of those dependencies have a vulnerability that is known. So as new known vulnerabilities get identified, you'll start seeing new vulnerabilities or new alerts after running a SCA scan on your code base. Developers use a variety of tools to help them in their work. Most important among these is the integrated development environment. That's a fact. If you don't have an IDE and you're trying to code, you're just making your life harder than it needs to be. But sometimes you make it harder. Sometimes if you make it harder, then you'll realize how much easier it is with the tools. Like recently I had to install, not had to, I chose to install IntelliJ on my work laptop. I had been using Visual Studio Code while working for a few weeks, but I used IntelliJ in my personal computer and my other project computers. So that was like the IDE that I was familiar with. But I think I installed Studio Code one time, or I just it was already installed one time when I was trying to write some code, and I just started using it as my default. But I realized it's not it's not something I'm familiar with. I'm not gonna say it's a bad tool, but I'm not familiar with it. So I was doing things and not having all of my workflows kind of my workflows weren't solidified as they would have been if I was using a tool that I was more familiar with. But even Visual Studio Code is better than using a note file or something to write Python code. That's crazy, but people do it. IDEs provide programmers with a single environment where they can write their code, test it, debug it, and compile it, if applicable. The IDE simplifies the integration of these tasks, and the choice of an IDE is a personal decision for many developers. I've used R like once, so I'm just looking at this to see like what's going on here. Many object-oriented programming. Many modern programming languages such as C++, Java, and the .NET languages support the concept of object-oriented programming, OOP. Other programming styles such as functional programming and scripting focus on the flow of the program itself and attempt to model the desired behavior as a series of steps. OOP focuses on the objects involved in an interaction. You can think of it as a group of objects that can be requested to perform certain operations or exhibit certain behaviors. Objects work together to provide a system's functionality or capabilities. OOP has the potential to be more reliable and able to reduce the propagation of program change errors. As a type of programming method, it is better suited to modeling or mimicking the real world. For example, a banking program might have three object classes that correspond to accounts, account holders, and employees respectively. When a new account is added to the system, a new instance or copy of the appropriate object is created to contain the details of that account. Each object in the OOP model has methods that correspond to a specific action that can be taken on the object. For example, the account object can have methods to add funds, deduct funds, close the account, and transfer ownership. I want to pause here real quick because it mentioned something very interesting. So, a lot of my time working as a software engineer, I spent building programs that were object oriented. When you're building an API and you're thinking about resources and you're like, get users or, get cart, put cart, whatever it might be. When you're building an application like that, it's more the component that you're building is more object oriented, especially if you're creating classes that represent data that's being passed either from your database to the API or the application, or between the application and the clients themselves. Whether your client is a like a user, like the laptop, phone, whatever, or your client could be some downstream application that you know uses the object that you gave to it. I think it's interesting to think about the fact that it said the other version of that would be functional programming and scripting. I'm about to look that up. Are functional and because I've heard of functional programming. Mm. So it's really just a functional programming. So functional programming, it's saying other programming styles, but talking to chat is saying that functional programming is a style, and scripts can be written using functional programming techniques. hmm And I'm even thinking about in an object-oriented program, some of the code you write is still going to be a script, especially if you're using uh, mm, like a modular programming style where you have like a repository layer or some database layer that's interacting directly with your data store. And then you can have a service class or a service layer where your business logic lives. Then you can have a uh, domain layer. Then you can have like a public layer where you're actually exposing the code or the functionality to the user through JSON or through HTTP, through GraphQL, whatever you choose to use at the time. But you could have functions that operate as functions and not specifically on or as a method in a class. It's like you can create a function, and usually I've created helper functions that if you pass an object to the helper function, it'll do something with the data inside of those objects. But it's not like I'm adding the logic as a method to the object or to the class itself. So that's like a difference I'm seeing. So maybe you can mix and match scripting, functional, and object oriented programming styles. And maybe you should to make the system work in the best way. Objects can also be subclasses of other objects and inherit methods from their parent class. For example, the account object may have subclasses that correspond to specific types of accounts, such as savings, checkings, mortgages, and loans, and auto loans. These subclasses can use all the methods of the parent class and have additional class-specific methods. For example, the checking object might have a method called write check, whereas the other subclasses do not. From a security point of view, object-oriented programming provides a black box approach to abstraction. Users need to know the details of an object's interface, generally the inputs, outputs, and actions that correspond to each of the object's methods, but don't necessarily need to know the inner workings of the object to use it effectively. To provide the desired characteristics of object-oriented systems, the objects are encapsulated, self-contained, and can be accessed only through specific messages, in other words, input. Objects can also exhibit the substitution property, which allows different objects providing compatible operations to be substituted for each other. Here are some common object-oriented programming terms you might come across in your work. Message. A message is a communication to or input of an object. Method. A method is internal code that defines the actions an object performs in response to a message. Behavior. The results or output exhibited by an object is a behavior. Behaviors are the results of a message being processed through a method. A class. A class is a collection of the common methods from a set of objects that defines the behavior of those objects. And it's saying methods, but uh, also members, right? So methods are only part of an object. You also can have variables that belong to that class. So if we're talking about an account might have a method that's called uh, write check or add funds. But you also have a member that's called account ID, account name, account opening date. Like those are characteristics of the object that aren't functions, aren't behavior. They're what are you information. Instance. Objects are instances of or examples of classes that contain their methods. Inheritance. Inheritance occurs when methods from a class, parent or subclass or superclass, are inherited by another subclass, child, or object. Delegation. Delegation is the forwarding of a request by an object to another object or delegate. An object delegates if it does not have a method to handle that message. Polymorphism. A polymorphism is the characteristic of an object that allows it to correspond with different behaviors to the same message or method because of changes in external conditions. So polymorphism is a characteristic of an object that allows it to respond with different behaviors to the same message or method because of changes in external conditions. I think this is similar to object overloading, or it's object or overloading. When you have a method that has the same name, maybe even the same output, or same same output pretty much, or like uh it'll return the same values or data type. But you can have, well, I think the best example of this would be in a constructor. You could have a constructor that takes no parameters. Then you could have a constructor that takes two parameters or more, right? So each one of those allows the object to be created, but it operates a little bit differently each time. Cohesion. Cohesion describes the strength of the relationship between the purposes of the method within the same class. When all the methods have similar purposes, there is high cohesion, a desirable condition that promotes good software design principles. When the methods of a class have low cohesion, that is a sign the system is not well designed. Cohesion describes the strength of the relationship between the purposes of the methods within the same class. When all the methods have similar purposes, there is high cohesion. Hmm. So I think that is this more like you shouldn't have unrelated code in the same class? Single responsibility principle. So this is something I was thinking about recently with some of my scripts. Some of my scripts are related to the same data, but I put them inside of different projects to make them easier for me to wrap my mind around. But I think this is like the whole point, single responsibility. If I'm creating a script or an automation to do something, it should only do that one thing. And I would have less repositories to manage if I put multiple scripts inside of the same project. But I could then start, you know, kind of tying things together that aren't necessarily related, right? Like the question would be like, how similar are these two functions or these two activities? If you're putting them in the same project, you should hope that they're very related to each other. But the more they kind of grow, the more likely it is that they'll start having different behaviors or uh, different features that would make them better to just separate. That's like the whole debate between microservices and monoliths. A monolith will work for a while, but eventually you may have to break it up just because of the way certain components mature over time. Coupling. Coupling is the level of interaction between objects. Lower coupling means less interaction. Lower coupling provides better software design because objects are more independent. Lower coupling is easier to troubleshoot and update. Objects that have low cohesion require lots of assistance from other objects to perform tasks and have high coupling.